So we've been looking at polygons and figures in a plane, curves, closed curves, um, angles. Then we looked at polygons which could be regular or not. So now we're going to extend those ideas into 3 dimensions and look at space figures. So when we go to 3 dimensions, we have an infinite number of planes. So by that I mean, if you pictured a building with bunches of floors, in fact an infinite number of floors, okay, all of those different floors in the building, all of the different ceilings, if you could extend them out forever, all of the different walls, there would be an infinite number of planes if this building went on and on forever. Okay? So if I think of a single plane in space, then that plane partitions space into 3 sets. The points on the plane and then 2 half spaces. So for a moment, imagine the surface of your computer screen extending forever up and down and side to side. Okay, then you would have in the space in front of it, that half space, you would have an infinite number of points. In the space behind it, you would have an infinite number of points. And then on the plane itself, you have an infinite number of points. Okay, so we have these 3 different sets of points. So when planes intersect, okay, they can be parallel or they can intersect at some line. So parallel planes, imagine the floor in the room you're in and the ceiling. Now if the building is constructed correctly and you haven't had anything that causes your floor to slant or your ceiling to slant, then those should be parallel. So if you were to extend them forever and ever, they would go forever and ever but never intersect. Now, if you look, suppose, at the wall in the room you're in and the floor in the room you're in, okay, they intersect. Now, if you happen to be in an A-frame house, it may not intersect at a 90-degree angle. Or like if you're in the Epcot Center, those sides do not intersect at right angles or acute angles. They will intersect at obtuse angles if you look at it. Okay, so when planes intersect, we call the angle between them a dihedral angle. So hopefully this is the case in the room we're in. The wall and the floor meet at a 90-degree angle. Unless you're in a place that's designed where it meets differently. If you lived in an A-frame, or if you look at the attic perhaps, if your roof is slanted, then they could intersect at an acute angle, or it is possible that they could intersect at an obtuse angle. But this angle, because it's between 2 planes, or we'll look at 2 faces, then we call it a dihedral. 2 for the di and hedral for the face. Okay, so you're going to measure that. If you're going to measure it, then you would measure it by the 2 angles where they intersect. Now we consider those and all these planes to be perpendicular to the line. They're not necessarily perpendicular to each other, but they are perpendicular to that line. So if they meet at a line, that's what we're talking about. And again, It can be obtuse, right, or acute. Now, when we looked at polygons, we started out with a figure in one dimension, line segment, and then looked at a union of those to get a polygon. Here we're going to start out with planes, a two-dimensional figure, and when we join planar regions, then we get a polygon, a polyhedra. So if we join polygonal regions, they can't just be planar, they have to be polygonal regions. The faces, in other words, have to be polygons. Then we get a polyhedron. Hedron is singular, poly, many faces. So this one is a polyhedron, okay? All of the faces, whether they're part of the pyramid part or the cubic part, then all of those faces are polygonal regions. They're all polygons. But remember, if we have a curve, then it's not going to be a polygon. So we only have a single face, we can think of it, but it's curved. So it's not a polyhedron. And here, this is not a polyhedron, because it has, basically, you can think of it as this face right here and this face in the back are not polygons. Because remember, these are not this is not one single closed curve. It's actually one with something taken out, and so it's not a polygon. So those, neither of those are polyhedra. Okay, so this has a curved surface. If it has a curved surface, it's not a polyhedron. If the sides are not polygons, it's not a polyhedron. Now, just like we could have convex or concave polygons, we can have the same case with polyhedra. Okay? This is not considered convex or concave because these are not simple closed curves on the front and on the back. So we'll first talk about prisms. Okay, and you've probably heard of prisms in your science class somewhere along the line. And it's important, if you can, to make sure students get a link between math and science. And a prism, okay, discovered that if you shine white light into it, the prism will divide up all the colors, separate all the colors in the spectrum that we can see in the visible spectrum. As the light is bent, then we can see a rainbow on the wall. And you could try it sometime. And if you've ever seen the movie Pollyanna, she gets a real kick out of crystals and prisms. So, when we have a prism, okay, we have two faces that are parallel. And if usually we set them up on their side so that the parallel faces are the top and the bottom. Okay, now these faces that are parallel are called the bases. Okay, in a rectangular prism, we could actually pick any two non-intersecting sides or two parallel sides as the bases, because they're all polygon, they're all rectangles. Okay, and then we have these other sides, which are called lateral sides, and lateral means sides. Okay, so we hadn't talked about pyramids, but just like pyramids, prisms will take their name from the shape that their base is. Okay, so here, and I'm still on this point, the base is a triangle, so it's a triangular prism. Here, the base looks kind of like a trapezoid, right? And so, and the top base is the same. And so that would be a quadrilateral prism. So you would name them, you know, as specifically that you can with, so you could call this a trapezoidal prism if you wish. Okay. If all these are congruent, then this would be a regular hexagonal prism. Okay, so you can have regular prisms or you can have prisms that are not regular. Now notice if, in the case of all these, if I were to set them straight up, they would be standing at a 90-degree angle on each side to the surface on which they're sitting. But that's not the case with this one. So if it isn't a 90-degree angle between the lateral faces and the base, okay, then we say it's an oblique prism. So this is oblique. So this would be an oblique pentagonal prism. If they do have the 90-degree angle, then that's a right angle. So these are right prisms. The other thing I know whether they're going to be a right prism or an oblique prism is if I look at the lateral sides. If all the lateral sides are rectangles, then it's going to be a right prism. If the lateral sides here are parallelograms but not rectangles, then it's going to be an oblique prism. Now pyramids are something we're all familiar with because of the pyramids in Egypt. And I'm not going to draw one because you'll see some pictures that are much better than my drawings. And in Egypt, all the pyramids are built with bases that are squares. Okay, and then the triangular sides rise up to a single point, a vertex. Okay. So that's just one type of pyramid. Just like we can have different types of prisms, we can have different types of pyramid. Okay. Now, in general, you can have any polygon be the base. Okay. And if you look at those nets that you folded into three-dimensional figures, you actually have a pyramid that has a triangular base. And we'll talk about that in just a second. Okay, but the sides have to be triangles. So just like we discussed with prisms, we use the base to name. So when we look at some examples of pyramids, okay, we have this pyramid, okay, which has a triangular base, so it's a triangular pyramid. This has a quadrilateral base if we knew that the markings, if we had specific markings, then that would be a square pyramid. And then this would be a pentagonal pyramid. And this would be 1, 2, 3, 4, 5, 6, a hexagonal pyramid. So we name them by their bases, but we also consider, just like we did for prisms, whether they are right or oblique. So if I were to take a chord and put it at this point, and this point is known as the apex, and let it fall, put a weight on it so it falls straight down, it would intersect the base right in the center of that base. This, however, if I were to drop a chord, it would not intersect in the center of the base. So this would be right, okay? In fact, these other two are also right. And then this one we call oblique. Now, the other way I can know by looking at these lateral sides is if the sides are isosceles, or that could be equilateral, because equilateral is a special case of isosceles, then it's going to be right. If it's not, if it's a scalene face, is a scalene triangle, then it's going to be oblique. And then again, like I mentioned earlier, all the lateral sides are apex. They meet at the apex, I'm sorry. They meet at the apex, the special point. It's the only point that's not part of the base. So we would say this is a right triangular pyramid. This would be an oblique, and we look at the base, square pyramid. Now we shouldn't assume that it's a square. You should have some sort of markings that indicate that. But sometimes they don't actually do that. So I could just say that this is an oblique quadrilateral pyramid if I wanted to. Okay? This would be a right pentagonal pyramid and a right hexagonal pyramid. In your lab, you had a set of nets that you were to fold into different polyhedra. And 5 of these are called regular polyhedra, or they're called Platonic solids. And Platonic is from Plato, right there, Platonic solids, not because he discovered them, but because he wrote extensively about them and their geometry. So when you folded them into 3-dimensional figures, you should have 3-dimensional figures where all the sides are made of the same regular polygon. So a regular polyhedron is a convex polyhedron, so it has to be convex, can't be concave. And their faces, its faces are congruent regular polygons. Okay? So I can think of this being regular, just like I thought of a regular polygon has congruent sides. A regular polyhedron has congruent faces. Regular polygons cannot be concave, and neither can a regular polyhedron. Now, the Greeks showed that these are all there are. You can't take any other regular polygons and put them together and they meet at the correct angles in order to form a different regular polyhedron. Now, the Greeks were really into shape and form and beauty, so you'll see a lot of Greek prefixes in geometry, and they were really into logic. So in the proofs in geometry, you'll also see a lot of Greek words. So looking at the Platonic solids, these are the names: tetrahedron, cube, octahedron. Now, we could actually say hexahedron. Instead of cube if we wanted to. Dodecahedron, octa here, dodeca, and icasa. So the Platonic solids are named by the number of sides that they have. So the tetrahedron has 4, and they have to be regular, so equilateral. Triangles for faces. The cube, now because a cube occurs so frequently in mathematics and in algebra, we don't call it a hexahedron. It's got a special name. It was called a cube probably before anybody called it a hexahedron or something like that. So it has 6 square faces, and you're familiar with that, like on a dice or on a set of dice. Those are both cubes. The octahedron has 8 triangular faces. The dodeca has 12 regular pentagonals. Now these should all be regular. I don't know why they weren't when I copied these. And the icasa has 20 faces, which are equilateral triangles. Now I gave you a couple, there were 2 or 3, I can't remember, that were semi-regular. So remember that a regular tessellation in the plane is made up of just a single regular polygon that's placed side by side over and over again without any gaps or any overlaps. Okay? A semi-regular tessellation contains 2 or more regular polygons that you could place side by side. You could tile the entire plane with them, but there were no gaps or overlaps. So semi-regular polyhedra are just an extension into 3 space of what we talked about in 2 space. Okay, so each of these are combinations of regular polygons. So, and you can kind of look and see some shapes like the soccer ball or whatever. Now, in your homework, you were asked some questions, but you can use your notes to do homework. As far as naming these, you will not be asked that on a test. Okay, but these are all actually called Archimedean solids. Wonder if you can guess Archimedean solids. Wonder who those are named for. Archimedes. And he proved that there's only, after you folded your nets in the polyhedra, then you were supposed to find a relationship between the faces and the vertices and the edges. Okay, and you did this for the regular polyhedron, and then you were supposed to check and see if this formula held up for the other shapes, for pyramids and prisms and things like that. And so you were to make a conjecture, and hopefully this was the conjecture you made, that the number of faces plus the number of vertices, which I have here, is equal to 2 more than the number of edges. And that holds for any type of polyhedron. An additional formula that I'd like for you to know is if you have a regular polyhedron, so this only holds for those, you can find the number of edges. So if you don't actually have one in front of you that you can actually pick up and count the edges, then you can use this formula. So the number of edges is the number of faces times the number of edges per face if it's taken apart divided by 2. So let's look at an octahedron. Okay, an octahedron has 8 sides. And each side is a triangle. So I have 3 edges, and I could say sides, I could say faces, but each of these 8 faces has 3 edges apiece if I were to look at all the triangles taken apart. Now, when I fold it, it turns out that if each edge is shared by two faces. Okay, so if you looked at, and I'm not going to do a very good drawing of this, I should have a little bit more confidence in myself, but I know I'm not very good at drawing. Okay, so we had this pyramid on the top and a pyramid on the bottom. Okay, so if I looked at a face here and a face here, these two faces, they share this edge. So apart, I count each edge twice. So I would take 8 sides times 3 edges per side, but when I put it together, I divide that by 2. So I'm going to get 24 divided by 2, or 12 edges, 12 edges for an octahedron. Okay, so all you have to know, if it's regular, is what the face is, what the shape of the face, and then how many faces there are. So you know how many faces by the name, and then the cube has squares, the dodecahedron has pentagons, everything else has equilateral triangles. So you know how many edges you would have on each face if it were apart. And then when it's joined together, you can find out by dividing that by 2, like here, and find the number of edges. Now we're going to look at a couple of cases of three-dimensional figures that are common, but they're not polyhedra because they have curved edges. Okay? So cones, of course, you're familiar with. Unless you go to McDonald's and try to get an ice cream cone. Never mind. Their cones aren't even cone shaped. Okay, so a cone has a circular region. Okay, a disc for the base. Okay, and a slope. It slopes up to an apex, just like the pyramid does. But it only has, really, you can think of this as just two faces. The curved face on this lateral side and the base. Okay, now just like we had right or oblique pyramids, which are basically the polygon version of the cone, then we can have also a right cone or an oblique cone. Okay, in the pyramid it was oblique. If I dropped a straight line from the apex down to the bottom, it would intersect in the center. If it was right, it would intersect not in the center if it was oblique. And then, if you think of a rectangular prism, its non-polygon counterpart, its curved counterpart would be a cylinder. Okay, so cylinders have bases. They're parallel just like they were in pyramids, but they're not polygons. And then they have this lateral side. And again, they can be right or they can be oblique. And then finally we have probably the most special type of curved three-dimensional figure, kind of analogous to the cube. We have a sphere. Okay, remember in a cube we have all the regular polygons. Here the regular squares. So you can think of it as the most regular of all shapes. But the Earth is not quite a sphere in shape, okay? But a sphere, if I look at a circle, if I look at a circle in 2 dimensions, Remember, the definition of a circle was all the points that are equidistant from a given point. But in a sphere, it's the same case, but it's not in a plane. It's in space. Okay. Now the Earth, as you know, is not quite spherical because of gravity and other things. Kind of throws it off a little bit. But it's a good picture of what a sphere looks like. Okay. So it's the set of points in space, not in a plane, that are the same distance from a fixed point called the center. So it's the three-dimensional equivalent to the two-dimensional circle. Okay. And then if you join the surface and its interior points, it's a solid sphere. I have used the word solid and polyhedra interchangeably, but I should make this clear. A solid is when you take all the points that are on the surface and you join the points on the inside. Whereas the polyhedra is just the outside faces. All those points. And again, the radius is the equal distance from all these points from the center in a sphere, just like they are in a circle. Okay? So, that length is the radius of the sphere. And then if you take a line segment through the center, in 3 dimensions, it could go, in any direction. You have the diameter, so twice the radius. So R, and that would be the diameter.